We have formulated weighted least squares. We haven't solved it, but we've formulated it. We've said that we want to favor certain data points by weighting their error, their squared error in particular, a little bit more or a little bit less than others. And again, that's on you to tell me what the weights are. Weighted least squares doesn't tell you which data points are valuable and which are not, which are trusted, which are not. That's you. You give me the data points, you give me the associated weights, and I'm going to turn the crank. And where we left off was just on the formulation. The formulation says we have an unknown u, think about this as slope and intercept, or the 3 parameters of a parabola, is equal to, well, here's the least squares from before, xu minus y, vector norm squared, and now we have this weighting matrix. Remember, this matrix is a diagonal matrix with the weight, an n by n diagonal matrix with the weight associated with each of n data points on that diagonal. All right, so what do we want to do now? We want to minimize it. Now the hope is that adding that matrix hasn't made a mess. Well, let's go find out. So let me write out, let me do that multiplication of the weighting matrix. So W is a matrix, it's going to multiply X, U, and Y. By the way, it's always good to go through these, especially in the beginning, to make sure that our matrices and vectors are multiplying the right thing. So let's do this. This is an n by n. What is X? It's an n by 2, so that matrix multiplication works. Those two inner values are the same. N by n is W. What is Y? N by 1 multiplication works. N by n, n by 1. Okay, just make sure that we're not doing anything goofy with these variables because they're not scalar value, they're matrices and vectors, and that only works if the matrix algebra is correct. All right, so now my quadratic error function is wxu minus wy, quantity squared. All right, let's differentiate. All right, the 2 comes out here as before, and we're, of course, differentiating with respect to u, so this term has to come out. And remember when the w wasn't there, what did we do? We brought out x transpose to make sure that the matrix multiplication works. And now what we have to bring out is wx quantity transpose. And remember that when you have a product of matrices transposed, that is the product of each of the individual matrices transposed. So Wx quantity transposed is x transpose times W transpose. That whole thing is going to be, the power reduces to 1, and then inside the parentheses is the same thing, Wxu minus Wy. So this looks very similar to before. We're just lugging around this extra matrix W, both on the outside here and on each of the individual terms. Of course, we're taking that derivative. We're going to set equal to 0 in the same way we did before. And now let's start to turn the crank to see if we can solve, make sure that W hasn't caused any problems for us. All right, let's see. I can drop the 2 again because I'm setting that equal to 0. So if I divide by 2, it goes away. So I've got x transpose W transpose times Wxu. That's that term right there. I've got x transpose W transpose times minus Wy. That's going to go to the other side of the 0. So I've got x transpose Wy on the right-hand side. All right, why did I move that over? Because, of course, that doesn't depend on u. This depends on u. So now what do I have here is I have this matrix over here. All right, what's x transpose? 2 by n times n by n, n by n, n by 2. Nice. That's still a 2 by 2 matrix, so I can invert it. Let's go ahead and invert it, and I have it right here. So now my solution, my weighted least square solution is x transpose, W transpose Wx, inverse, x transpose, W transpose Wy, and I have a closed form solution for a weighted least squares where W has the weighting along the diagonal. Let me simplify this a little bit and then make sure that this actually makes sense because there should be a relationship to least squares. Let me define W2. Remember, W is a diagonal matrix. What's the transpose of a diagonal matrix? It's the matrix itself because the rows and the columns, nothing changes when you transpose. So that means when I multiply a diagonal matrix times another diagonal matrix, all I'm doing is squaring the diagonal elements on the matrix. And so if I call W2 the square of the weights, I can just simplify this notation here so I don't have to lug around a W2W and a W2W here. And now my weighted least square solution is x transpose, weighting matrix squared, x inverse, x transpose, weighting matrix squared times y. Now, here's a question we might want to ask ourselves. What happens if the weighting matrix is the identity matrix? Well, first of all, what does that mean to be the the identity matrix, it means the weight associated with every point on the in the data is exactly equal. Yeah, we're not favoring one or the other, right? So what happens when I put this weighting matrix into this weighted least squares? All the weights are equal to 1. Well, let's see. If I have an identity matrix here and an identity matrix here, well, then it just goes away. And so what are we left with? We're left with U is equal to X transpose X inverse, X transpose Y. That's just least squares. That's nice. That's nice, in fact, because basically you can think about everything being a weighted least squares. It's just that we're weighting all the points equally. And if we don't want to weight the points equally, well, then we just throw everything into a diagonal matrix here. So notice that this is a soft implicit assumption, but we were assuming that basically all the data points are the same. And often that's the case, but often it is not the case because sometimes you have more reliable data. Sometimes you care more about certain parts of your domain than you do in other parts of the domain. And this weighted least squares, assuming you have a mechanism for determining the weights, gives you a very nice way of generalizing least squares estimation to take that into consideration.